All right. That's I started the recording, and let's get started. If you want to turn on your webcam, that would be great. Because I was using this technology is good, except a couple issues. The most important I saw is the feedback, because when the instructor is talking in a real classroom, I got instant feedback, like you guys fall asleep, something. But here, I watched one instructor is talking to her class, almost no sound, so nobody hear her talking, and there's no feedback. So yesterday I was having another class. I was using this, and it's getting too heavy, and I took it off. And then one student was trying to ask questions repeatedly, and I didn't know, so there's no feedback again. So yeah, I would really appreciate if you are convenient for you, just turn on your camera and turn on your mic when you want to ask questions. So I'm assuming everybody hear me all right.
Yeah, I can hear you.
Perfect. Since we missed one class on Monday, so I will go through a little bit of course material before today's lab, because the lab is related to the material we're going to cover right now. So Monday, we're supposed to cover this topic of active device. So last time, if you remember, we ended right here. Let me switch cameras. Okay. So last time we kind of stopped here. So that's a filter we can design, and it's called passive because there's no amplifier. If you see the circuit, it's all resistors and capacitors. So today we're going to introduce a new device. This device is very common everywhere. If you talk about electronics, you're looking at amplifiers. So we're going to cover amplifier. If you major in electronics, you probably already spend the whole semester or 2 semesters on amplifiers, which is anyway. This will be eet452, and the course before that will be eet412. So you spend 2 semesters on this little device. Instead of spending 2 semesters here, we will be spend 10 minutes. So obviously, we will just have a very, very brief, because we only have 10 minutes to introduce this device. Well, op-amp is a device which has 3 terminals. We have the positive inputs, have a negative inputs. That's a positive input. That's a negative input. That's the output. So this is a typical 3-terminal operational amplifier. And the input and output is the output equal to the positive minus negative multiply the gain. So that would be the output. The out equal to gain multiply V positive, subtract V negative. So that's our op-amp. And how much is the gain? Generally is in the tens of thousands, if not millions. Tens or hundreds of thousands. So it's a huge amount of gain. Tens of thousands. Hundreds of thousands. So that's an op-amp. And how do we use op-amp? That's our next topic, section 5. The next topic, section 5, we will cover the various ways, method to use op-amp. Number 1 will be voltage follower. So this is the amplifier, the gain is 1. Gain is 1. So that means the output equal to the input. So whatever input you have here, the output will be identical. So it's a unit gain amplifier. The gain equal to 1. So they are identical. So that's first one. Why we want to do it? We didn't change it, make it bigger, but we make it stronger. What do you mean it's not bigger? The voltage is the same, but the current is bigger. That means stronger. So this amplifier make the current stronger. Although the voltage is identical, so input is 1, output is 1. But this output can drive a big current compared with the source. The source can be an antenna, for example, which only has voltage, no current. So that's one way to do it. Make it stronger, not bigger, but stronger. The second application will be the inverting amp. That's a typical inverting amp. You don't need 2 resistors. These guys amplify 2 signals. I don't really like that. I want to make it simple, so you don't need that. So just have 1 signal. The output will be amplified. So that's what the inverting amp looks like. Inverting amp. So this is the op amp, and the out equal to R2, R1. Negative. So this is the inverting amp. The input signal goes to the negative terminal of op amp, and the output is this is called a gain. So that's a gain. Depend on the ratio of 2 resistors. If we have 10K, 1K, that's the 2 resistors. The gain will be 10, negative 10, for example. So this circuit will make it 10 times bigger, also stronger. So that's an amplifier with a gain of 10. All right, many other applications. Fortunately, first, for electronic students, you already know it. So I'm not going to waste your time. Like I said, I only plan to spend 10 minutes. Second, for manufacturing students, all you need to know is what you want to achieve. So this amplifier basically can change the gain. Yeah, make it stronger and bigger. So that's what you can achieve. And then the design can be done by computers. So you can actually, there's a computer programs can help us design something like this, or something like this, or something like this. All you need is a requirement. If you do not know computer, you can just hire an engineer, electrical engineer. Well, any electrical engineer can do it. So it's simple. It is an old subject, completely thoroughly analyzed 50 years ago. So nobody wants to spend too much time on this. So that's op-amp, and that's our introduction before the lab. So today we're going to do a couple of op-amp labs. We will first do it on multi-sim. So we will first do it on computers. And then we will switch over to this op-amp right here. We will switch over to the real world, and we will find out the differences between the theory and the real components. That's very important because everybody needs to know the differences, because we are engineers, technicians. We are not theoretical people. We are practical. Everything is practical. So we are important to know the difference. There are three major differences from theory to the real thing, from the theory to real thing. So we will talk about that on the second half. The third part will be an assignment. The assignment will be just like the assignment for previous week. It will be a computer simulation. You guys will do it and take a screenshot and upload your images to Canvas. I already checked out last week's assignment. Last time I checked, I have 9 students finished assignment. Hopefully we have more today. Okay, let's get started. Number 1, computer simulation or multi-sim. Let's switch cameras, switch my share. Let's do a computer simulation. So this is a multi-sim live, same as we used last week. I have a couple of circuits. We started with the first one. It's a week 4.1, so I will open this. Open the circuit. So this circuit is a voltage follower. That means the output and the input are identical. So let's try it. To simulate, all you need is to push this button. It's called run simulation. So let's run the simulation. And again, I prefer to see the results and the circuit side by side. So this is side by side. And what you'll see is you got the inputs and the outputs identical. Both are -1, so they overlay. So what you'll see is the channel 1 and the channel 2. Channel 1 is the green, which is the inputs. Channel 2 is blue, which is output. They overlay each other. So you kind of you cannot see channel 1 because you cannot see the inputs because the input is completely covered by the outputs. So that's called a voltage follower. Input output identical. Voltage follower is very easy. All you need is one single wire from negative to the output. You connect the output to the negative inputs. That's all you need. You'll have a voltage follower. So that will be our first one. Let's look at the second circuit. The second circuit will be inverting amp. Inverting amp. So this will be inverting amp. Oh, this is a non-inverting amp, not inverting. So this circuit is a little different from the circuit we have just discussed, which is inverting. Well, a lot of people don't like the negative gains, right? We don't want negative gain. We want a positive gain. So this is a positive gain. So this is called the non-inverting amp because the input signal goes to the positive terminal inputs. What about the gain? This is R2 to R1 ratio is 10. But this non-inverting gain, the gain is actually 11. It's always 10, the ratio plus 1. The ratio of those two resistors plus 1. So the actual gain will be 11, positive 11. So let's do the simulation. So input is 1, out should be the positive 11. All right, again, we do the simulation. Again, you see it right here. The input is 1, output is 11. So input is the green, little one. The output is the bigger one. All right, that's a little bit better. So let's stop the simulation. Okay, let's stop. So that's my inputs. And that's my output, which is 11 times bigger. 11 times bigger. If you look at the inputs and outputs, they are perfectly identical. So that means no distortion, no distortion. Everything is perfect. Everything is perfect. So your input is small, output is perfect and big and strong. That's, in theory, that's the ideal world. So what happens in real world? What's the difference if I want to build a circuit like this? So here is the identical circuit I built. So that's the computer simulation. Everything is perfect, beautiful, nice, no problem. But what about the real components, real circuits? So now I will stop this and we will change over to the real op amps. So let me change my camera again. So this is a real op amp. It actually has two inside, 2 op-amp inside. It's a 3-terminal. So that will be my positive input, pin number 3. Pin number 2 will be my negative. Pin number 1 will be my output. So this, I use the bottom half. I didn't use the top half. The top half have another op-amp. I only use the bottom half. That's 1 op-amp. The circuit is identical to the non-inverting amp we just studied. So the input will be 1. The gain will be 11. So if my input is 1 and the gain is 11, the output will be multiply 11 will be 11, right? That's in theory. So let's find out what will happen. So this will be my input. This yellow wire will be my input. It goes right to the positive if you look at my input. It's a sign, goes from negative to positive 1. It's a sign. And the output is this red wire. That's my output. Goes to oscilloscope. So that's it. Input and output. Input is here, output is here. The red wire is my output. And this is my op-amp. This is the battery, power supply, positive and negative. So I will start the power, start everything, and you guys will look at all the instruments. So I will switch camera again, and for you to see the instruments. So first I need to turn on the power supply. So that will be my power supply. The power supply will be positive and negative 5. So this op-amp can work with positive 5 and 0. That means a single power supply. And also works with a dual power supply. That means positive and negative 5. So that's what our setup is. So we have positive 5 power, we have negative 5 power, goes to the op-amp. So that's number 1. Number 2 is my input signal, 1 kilohertz. So I will have 1 kilohertz sine. The amplitude is 1. So it goes from the positive 1 to the negative 1. So that's a negative 1, the voltage. That's positive 1, the voltage. So I will turn on the power supply. I will turn on the signal, and then I will turn on the scope. So that's my input, the yellow, between the negative and positive 1. That's it, the yellow. And the blue will be my output. What's wrong? The blue is first, it's not sine, you know. Second, it only goes to positive 3.7 maybe, and it goes to negative 4.5, right? Negative 4.5. So that's the number 1 problem. Problem number 1, we call it saturation problem. Saturation. I will change my camera so you guys can see the camera. Where's my... Now that's another complaint I have for this software. It's the control is all over. All right, now you'll see the camera. I hope. The number 1 issue is saturation. It will saturate on both sides. Saturation on both sides. What is the saturation? That means the output, the power supply is positive 5 and negative 5. That's the power supply. And the output can never be bigger than this. The output can never be bigger than positive 5 and negative 5. So right now, the output is trying to be positive 11 and negative 11. There's no way you can get output positive 11, negative 11. And the maximum you can reach is, look what we have here, positive 3.7, negative 4.5. So that is the maximum positive and the maximum negative. So that's called saturation. So in order to solve saturation problem, all we need to do is go back to the generator and make our input signal smaller. Now I make it smaller, 300 milli. Let's look at the scope. Now we are talking, right? So now there's no saturation. Why? Because I lowered my input signal. If input signal is too big, it will saturate on this side, And so input signal have to be smaller than 300 milli. If the input signal is stronger than 300 milli, it will reach a flat plateau right here. And the bottom also same thing. So you will see the saturation. You also call the cutoff. You have a positive cutoff. You have a negative cutoff. Right now, there's no positive cutoff, no negative cutoff. Everything looks good. So that's the issue number 1, saturation. Issue number 2. Well, right now, input is 300 milli, output is, that's 0.3. So 0.3 multiply 11 is 3.3. So that's no problem. Multiply 11, so gain is 11. What happens if I increase my frequency to 50K? So now, my signal is the same strength, 300 milli, but I only change the frequency. So it's higher frequencies. So let's look at my output. You noticed the input is the yellow is still the same, but the blue is much smaller. Blue is much smaller. So the input, that's my output. Notice what? The gain is about 2, not 11. It's supposed to go to here. The blue signal supposed to go here. But now the blue signal only reaches that level. So it's a severe gain loss. So the number 2 is a bandwidth problem. The amplifier only amplifies certain frequencies. There's a bandwidth limit. And this bandwidth limit, so if I change to 25K, that's what happens, 20K. So if it's 20K, wow, the gain is a little bigger. So the gain is now 1.5. That's the input, that's my output. And the gain is 1.5 divided by, so the gain 1.5 divided by 0.3 is a gain, instead of 11, the gain is 5. Right now the gain is 5. So the gain actually changes with frequency. That's the frequency. And that is the gain. So it's kind of look like this. So this is called a Bode plot. So the Bode plot is the plot of my input frequency versus gain. Input frequency versus gain. So how can we get the both plot? One way to do it is do a lot of testing. So you change input frequencies, 1K, 2K, 3K, 4K, right? And you measure the output gain and then you plot it. That's one way to do it. Alternatively, we have an instrument called boat plotter. Boat plotter. The boat plotter is an instrument just do that. So this is a boat plotter. And that's the horizontal is frequency. That's 1 megahertz. 1 megahertz, 200K, 100K, 20K. Right now the gain is 5. 20K gain is 5. 10K, the gain is about 10. So let's look at 10K. 10K. And let's look at my outputs. Yeah, that's about 3.3. Yeah, the gain is almost there. 10K. Okay. So for 10K, the gain is about that's 10K. The gain is about 10. For 1K, right here, 1K, the gain is 10, perfect 10. So for low frequency signals, so what is the bandwidth of this amplifier? We use negative 3 dB as the indicator. So let's look at let's move this marker right. Oh, not this. This is 3 dB. Negative 3 dB is an important concept. So right now we are pointing at negative 3 dB decibel. Negative 3. If you remember last class, oh, it's a different class. Negative 3 dB. So at negative 3 dB, that will be the bandwidth. So my frequency is 12K. So 12.9K. So the bandwidth equal to 12.989K. Well, we just say 13K. So this is the bandwidth of my amplifier. So number one issue is saturation. Number two is bandwidth. So if you want to have a amplifier, the input frequency in this case have to be below that frequency. Anything above will be greatly attenuated, reduced the strength. So it only works for 13K or less frequency, input frequency of 13K or less. So that's good for audio. For audio, that's no problem. Our human voice generally is below 6K. And as a matter of fact, a lot of our hearing are so damaged, we can't hear anything about 10K. A kid or baby with a brand new ear may hear up to 20K. But as adult, our hearing loss is very gradual. You don't really notice it, but it's there. So this is the bandwidth. What is the third problem? If you look at your oscilloscope, let me stop it. Notice what? There is distortions. So third problem is distortion. Well, in an ideal world, when we do computer simulation, input and output is identical. The only difference is strength. The only difference. But unfortunately, in the real world, Never happens, never happens. So the input and output, yeah, that's your input and output. So input is the yellow perfect sine. It came from a function generator. That perfect sine, 300 milli, negative 300 milli, positive, negative, positive. The output is 3.3 positive, negative 3.3 positive. The gain is still 11. That's not a problem because the signal right now is 10K, 10,000 hertz. So 10,000 hertz is no problem because the bandwidth is 13,000. So now we have 10,000 hertz input signal, no problem. The gain is still 11. Look at here. Well, this distortion mostly happens on the negative side. That is actually designed that way. This op-amp generally only works for single power source. That means 0 to positive 5, 0 to positive 5. And this negative part is generally not used on this amplifier. So the distortion happens on the negative side, not a big problem. Majority of the, less distortion. The distortion is a problem if we want to use the negative side, but fortunately, we only use positive side. So this distortion is a design problem for op-amps. All op-amp has this, it's called crossover distortion. It's called crossover. The crossover distortion this time happens in the negative side. Generally, it happens right here between the positive and negative. So the crossover distortion happens when the op-amp is switching from positive to negative. Why? That's because the design of the op-amp. So a crossover problem can be reduced, but never eliminated. So we can design better circuits, better op-amp to make that crossover less and less a problem, but it will always be there. So that's the first crossover distortion. The second distortion happens when I increase my frequency to 50K, and we notice the huge distortion. Huge distortion happens. So that's my input perfect sine. The output, not only we do not have any gain, we have 0 gain, looks like. Maybe not 0 gain. The gain is about 2. So that's more like a realistic. Right. Okay, that's more realistic. So my input is yellow. Output is blue. The blue is about twice as big. So yellow is 0.3. The blue almost reach 0.6. So the gain is about 2. So there is a little bit of gain at 50K. The gain is not 11. And if there's no distortion, we should have a perfect circle here. It doesn't look like a circle, right? It's a kind of ugly shape. Also, you can look at here. It's a lot of distortion on the negative side. And also positive side has distortion. So a lot of distortion, not because the crossover problem. Actually, here we are not worried about crossover. It doesn't reach the crossover happens right here. We haven't reached the crossover point yet, but we still have distortion. So that's called a harmonic distortion. Harmonic. Not only have crossover distortion, we also have harmonic. So we have 2 distortions. We have a crossover distortion. We have a harmonic distortion. How do we measure harmonic distortion? We will use another instrument. So let me get one more instrument. It's called the spectrum analyzer. Actually, we don't need that instrument. We just use that on our scope. So let me turn this off. Turn the XY off. So that's my input and output. Let's look at the spectrums. When we look at spectrum, we mean looking at the signal in frequency domain. So when we do a FFT, so that's what I'm talking about. So this is 1K. The yellow, if you look at the spectrum of yellow, the spectrum of yellow only have one energy pulse at 1K. That's 1K. Oh, 50K. I'm not, right now my input signal is 50K. So not 1K. My input is 50K. If you look at this generator, generating 50K. So the input is 50K hertz. So if I look at my spectrum, the input, there's only 50,000 hertz energy. So that represents the energy of certain frequencies. There is only one energy, that's 50 hertz. So this is a perfect sign, because there's no other energy. Those are the noise. There's only one energy at 50,000. That's perfect sign. But what happens if we look at my outputs? My output, notice not only I have 50,000, I have 100,000. I have 150,000. If I keep looking more, I have 1, 2, 3, 4, 5, 6, 7, 8. They have a small guys over here also. 1, 2, 3, 4. That's 4 is 200,000, 25,000, 250,000, 300,000. So it has all those. Notice the frequency is multiple. So if the input is 50, multiply 2, multiply 3, multiply 4, that's 200, multiply 5. Those are called harmonics. So this distortion appears as a harmonic. So that's why it got the name. The distortion, the reason for distortion is because the output has too much harmonics. So the distortion is measured by total harmonic distortion. Total harmonic distortion measures this guy, measures harmonic distortions. The definition of total harmonic distortion is that all those energies adds up, divided by the base energy. The base energy is your 50,000 hertz. 100, 150, 200, all those energy adds up, divided by the energy on the base. That will be a total harmonic. This will always be provided by manufacturer. The manufacturer will provide the total harmonic distortions. Now the total harmonic distortion will drop as we reduce frequency. So let's go back to here. Let's change it to 1000 hertz. So if my input is 1000 hertz, now it's 1000 hertz. So if I look at the scope, 1000 hertz. So if I'm looking at 1000 hertz, let's look at the input signal first. Only 1000 hertz, right? Right here, 1000 hertz. That's 1000 hertz. The spectrum of my input, 1000 hertz. The distortion will be a little bit better, but it still have distortion. So let's look at my harmonic distortions. Yeah, 1000, 2000, that's called harmonic. This guy is called second order harmonic, third order harmonic, fourth order harmonic. Let's keep looking. This guy is called the bass, original, 1000. Second order harmonic. This is not supposed to be there. An ideal amplifier, the output should only have 1000 hertz. That's in the ideal world. In the real world, when your input signal, which is 1000 hertz, pass through this amplifier, not only you got 1000 hertz, you got 2000 hertz, 3000, 4000 as outputs, 4000, 5000, 6000, 7000, 8000, the last one, 8000. It keeps going on forever. So those energy all adds up as total harmonic distortion. So to sum up, the difference between the real and the difference between the real world and the ideal world, there are many differences. The first difference will be saturation. That's my first difference. The second difference will be the bandwidth. The third difference will be distortions. So there's always distortions after the amplifier. There's always bandwidth limits. There's always a saturation potentially if your input is too big and you saturate the outputs. So those are three issues, most important. There are many others, by the way, unlimited issues when you work in the real circuits. But those are the three big ones I want to demo here. So is there any questions anybody want to ask? I talk 50 minutes almost.
So
you guys to talk. Yes.
The bandwidth, that's just the related to the frequency, right?
Yes, exactly. Perfect.
Okay.
Yes, it limits what kind of frequency the amplifier can handle.
So, and the whole time that you were messing with that program, that was actually taking measurements on the hardware that you had showed us earlier, right?
Yes, you got it. It's a real circuit measured. It's not simulation. Excellent question. You might wonder how I demo you guys with a real instrument. Everything is here. This is the best technology. It's called Analog Discovery by Digilent. If you have $300, buy one of those. It's the best technology in today's virtual world. Basically, it's a one box replace 20, if not 100 instruments. It sounds too good to be true, right? Sounds too good to be true, but this time it's true. Analog Discovery. It's the best technology. It will provide everything electronic, instrument, the function generators, the power supplies, everything you need to test a real circuit. This box is the real thing. You can teach the whole electronics curriculum from high school to PhD. Yes. Other questions before we go to assignment? So any other questions before we move on to assignment?
That's all I have.
Okay. Somebody else. Jeremy, yesterday I didn't hear your questions. Give me a question today.
I don't think I have a question too. Actually.
All right, no questions. Let's move on to the assignment. So the assignment today will be from the textbook. It will be 100 and page 105, if I remember. Yep. So this will be today's assignment. So this circuit right here on page 105. And what you require you to do is simulate this circuit on multi-sim. So what exactly does this circuit do? I will demo it here. I just did it right before the class. So let me show what this circuit do. So let me go to the circuit. So this is the assignment circuit. Okay. So if you look at the circuit, it's a little different than the circuit we have in the book. The resistance is 1K, 1.9K, 1K, 1K, and 2K. This is the big difference here. The resistance here changed to 2K. It's 1K, 1K, 1K. And everything else will be the same. This is the battery. This is another change here. Battery will be 4.6. Instead of, in the textbook, there's no battery here, but we use a battery. Another change, the textbook, if you look at the textbook, there's another amplifier, a voltage follower. We skip that voltage follower because it's unnecessary in this simulation. So what exactly does these circuits do? Let's turn the power on. So this means turn the power on. And look at the simulation. So this is what the circuit do. The input is blue, the output is green. So these two op-amps will first make our input stronger, right? The input is kind of small and weak. Now it's 0 to 5. That's the first change the circuit does to our input signal. The second change is it's shifted our input from negative 2.4 to 0. Also shift the negative 1.1, that's negative 1.1 right here, to positive 5. And now we have a standard voltage input to my controller. So assuming the input came from a sensor, so they are measuring temperatures. This is the lowest temperature, this is the highest temperature. The sensor output will be negative 2.4 to negative 1.1. But my controller do not like this signal. My controller wants 0 to 5. So that's the lowest temperature, that's the highest temperature. So this circuit will do analog reconditioning. So this circuit demos analog reconditioning circuits. So that's the initial, that's the results. The result will be a perfect signal to the controller, goes from 0 to 5. So as temperature goes up, temperature goes down, temperature goes up, temperature goes down. This will be my sensor. Temperature goes up, temperature goes down. So this sensor is using a power supply to simulate my sensor. So this is a triangle voltage power supply. You have to change my VA to 1.3, change VO to negative 2.4. So that will simulate this guy. So this will be the negative 2.4 right here, negative 2.4. This 1.3 will be help the sensor to reach this level. So plus 1.3 equal to negative 1.1. So the difference is 1.3. So that's the difference between the negative minimum and the maximum. You put it on VA. And of course, you need to build a schematic, build a circuit like this. You need 2 amplifiers, couple of resistors, power supply here, a battery here. You need 2 voltage indicators, one here, one here. And then when you do the simulation, and you have a dynamically displayed inputs and outputs. So when you finish the lab, take a screenshot of this picture and again upload it to Canvas. That's our assignment. So any questions with that assignment?
No, it sounds easy enough.
Yes, that's a very easy one. You can do it now. I would prefer you do it now. You take a screenshot and upload it. I will create an assignment right now. So while you are doing the simulation, you can do it later. You have 1 week.
I'll just do it now.
Yeah, you do it now. Take a screenshot and upload it to Canvas. Okay. I will be here to answer your questions. That's one advantage of doing it here. Okay. All right. If we do not have any questions, I will stop my recording. And hopefully, people not here, we only have 5, 6, will watch my recording and complete lab that way.